session. Okay, here we go. All right, so um, because today's lecture is, I think it's we can count towards like maybe we should have like about 24 sessions in one trimester, and this is already at our 20th, so we should have 4 more lectures, and that should fit our schedule quite all right. I think quite all right mean I think next week is going to be our last week of, I think so, right? Is that last week of lecture? Yeah, like next week. Okay. And the week after that will be exam week. All right. However, because for us, we can take exam at any time because it's going to be the take home. And in general, you guys can pretty much pick as late as you want. So that means we're going to have, I would say, I would call it like not including this one. We have 3 more lectures. Sounds like a plan. Okay. So what we are, I'm going to propose is this. So we're going to see each other again on Monday and Wednesday. That's a regular time. And then we're just going to have one more um, um, makeup for, so there will be total of 3 more lectures to cover the materials. And then I will pretty much like save one session for the day before our final exam. Sounds like a good plan. All right. In case that like you go through the studying and everything, and then you would like to sort of like stop by and just like what we have done in the past 2 exams. So we'll have like Q&A sessions, or we have a review questions session and everything. And then we'll do the final exam the day after. Okay, sounds like a good plan to you guys. So including this lecture, there will be 3 more. I mean 4 more lecture. That should cover quite enough, I think, because as you have seen, this last portion is getting crazier and crazier, and that is about to happen even more today. It's happening. I think this is sort of like the peak of the course right now, where the complexity of mathematics is at the peak. It's right here, around here. You're getting there, but it's not that bad. I'm just saying that in terms of like, it just sort of like unfamiliar. That's all. It's not like super difficult or anything, but it just requires a little bit of time to get used to. Okay. All right. So let's finish the business that we sort of left last time about the electric potential. Okay. So what we are going to try to do today is I'm going to show you how this electric potential works and how can we use the expressions for finding out the electric potential from like this one, from a point charge, or even from the fundamental relationship between the field and the potential difference to calculate the potential. Okay, so I'm going to show you how it's done. And we have plenty of examples today. So I hope that you should be able to sort of like, get a feeling of things to come. Okay, here we go. So just, I mean, this one we already commented last time, but just want to comment again because you're going to have to see this phrase many, many times here. Okay, every time that you would like to use this relationship right here, V equal to KQ over R square is a potential from a point charge Q. You always assume this, at least now at this point. So you always assume that the potential to be 0 at infinity. Okay, and this sentence has to be sort of like stuck with this formula at all times. So you will see in examples. Okay, so don't worry too much about this. It's just our agreement that if you would like to use that expression, it means it's the potential of that point charge with respect to or in relative to the potential of 0 at infinity. Okay, that's all. Okay. All right. Oh, I didn't read the comment. What is that? Final countdown. All right, getting there. All right, and the good thing about the potential, now you understand from last time, it's just it's sort of like a sibling of energy. So when it's sort of like an energy in a way, it's path independent. Right? In physics term, we call it, it has a root in the conservative force. So this means electric force is a conservative force, just like gravitational force. Okay, so that's good. So that's a good thing is if you come in a closed loop, there will be no change. Okay, everything come back to the original position. The energy that you have is going to be exactly the same. All right, let's get to it. So let's use this example as a warm-up question. Let's see. The figure shows four arrangements of charged particle, all the same distance from the origin. Okay, looks good, everything. Rank the situations according to the net electric potential at the origin. They want to know what is the net electric potential. Most positive first. All right, here we go. So because right now, as you can see, when we talk about potential, just like gravitational potential, you have positive value, you can have zero value, or you can have negative value, and you don't have any direction. So what we are talking about right now is potential is a scalar quantity. So that means it could be positive, zero, negative. These are all scalar value. Okay, sounds good? All right, so they want the most positive down to the most negative. Yeah, the smallest one. Okay. And this sentence is just showing up right here. Take potential to be zero at infinity, of course. When you look at this sentence, you think in your head, of course, I'm going to use this, KQ over R. That's worked perfectly fine with this condition here. Okay, so this is how it's supposed to be done. So if you look at figure A, you would like to figure out the potential at the origin due to now you have only two charges here, positive 2Q, negative 9Q. So what you think is you just do one at a time. So let's start from the top right here. Let me call it number one. So you look at the origin and just ask yourself like, hey, how much potential I'm going to be able to obtain from this positive Q charge? So it's going to be, let me call it V1, it's going to be K, that Coulomb's constant there. The charge now, because we are looking at the magnitude, the positive charge will generate positive potential. Negative charge will generate negative potential. You guys with me? Okay, the sign now is important because it tells you the level of the potential. So in the formula now, you need the sign into it. So this is unlike what we did with the electric field. In the field, you sort of like separate your calculation into two parts, the directions and the magnitude. The direction, you just consider the type of charges, like, okay, the same type, they repel, opposite types, they attract, and then, okay, you're done with the directions. And then you turn your attention to the magnitude. So when you look at the magnitude, oh, I don't care the positive or negative. I want to just take the magnitude of it. So that's why when we did the field, we didn't care so much about the sign when we were trying to calculate the magnitude. Sounds good? But now we want the value of the potential, which could be positive, negative, or zero. So that's why now the sign of the charge is crucial. You need it. So I have to put 2Q with the positive sign in here, divided by, now that just the distance from that charge generating the potential to the point of interest. And that's, okay, you can call it A for now, and just say some distance, A down here. And that's it, you're done. Don't need to square anything because that's, you already did it. Sort of like you arrived at this equation or this formula from the integration. So the power is dropped down by 1. You only have the distance underneath, and that's it. Okay, sounds reasonable? Okay, try again. You have another charge. Let me call it number 2. So you say the potential at the origin due to the charge number 2 is going to be K minus 9Q. Yeah, I take the negative sign along with me. Divided by the same distance here. That's what they said. A. Now, what you get at the end is the net electric field. I'm sorry, electric potential at the origin is going to be just V1 plus V2. That's just a simple summation now. That's it. It's a scalar quantity. And that's it. So you say it's going to be K plus 2Q over A plus K minus 9Q over A. And that's it. You can just add things together. It's negative 7. So it's going to be negative 7KQ over A. And that's it. You're done. Okay, sounds good now. So I hope by showing you this is the way to do. And you're going to do this again and again and again in every other cases. For example, try the second one, part B. You would like to figure out the potential at the origin. Now you should be able to do like very quickly. So what I can do is I start from the left one I'm going to get, okay, let me do this case B. I'm going to say that the total V is going to be K minus 3Q over A with me. All right, and move on to the next one, plus K negative 2Q over A. Good. And then at the next one, you're going to get is negative 3, negative 2 is going to be negative 5KQ over A. Cool. Done. Try again. Let's do part C. Okay. Here we go. Now you have 3. So let me go like from the top 1 and then followed by the 2, followed by the 3, followed by the 4. 1, 2, 3, 4. So all you need to do is just keep doing. But the good thing about this problem is you can see that all of the charges are at the same distance from the origin. Now you start to see that there is a common factor in the front, K over A, K over A, K over A, K over A. So you're going to see this K over A from all 4 charges now in part C. So actually I can pull that one out if I want. It's a common factor. So the total V is going to be K over A in the front. And all I need is just sum all the charges. So I can see minus 2, minus 1, minus 2, minus 2. Total is going to be minus 7Q. You guys with me? So just after a couple of sort of cases, now you know how to do it very quickly. And that's it. So the potential at in the C case is going to be a negative 7KQ over A. Cool. And from here, you should be able to do part D in a similar manner here. It's going to be K over A, common factor. And then all you need to do is just minus 4 plus 2 minus 7 plus 2. That's nice. You still get negative 7Q anyway. And that's going to give you the final value right here. Done. Okay, so in conclusion, this is your final answer. It looks like this. The first case, the potential is negative 7KQ over A. Part B, negative 5. Part C, negative 7. Part D, negative 7. So it turns out A, C, and D having the same value of the potential. And it's the lowest. So the most positive, yeah, is going to be right here, part B. It's just only negative 5. And as you can see, all these 4 cases give you negative potential. Net. Okay. See, not bad. It's actually easier because you don't need to worry about directions. So actually potential, personally, I like it better. Because it's just number. You just have to add, subtract, whatever, a little bit. All right, that's a question I missed. Can you draw? Can you explain this in 3D drawing? Why? Drawing something like 3D distribution of the potential. What does it mean? Yes, I can, but let's do that a little bit. Oh, I think they dropped that one down already. Maybe. Well, I'll think about it. All right. If you guys sort of like not too confused about what we are doing, I might be able to explain to you using the 3D. Well, it's a 3D plot, but it's still sort of, yeah, you can think of it to 3D. Yeah. All right. That can be done, of course, if you like. It's actually, I used to have some vector calculus based on that 3D plot too. So that's actually is a good question, but I just dropped that part of the material. Okay. All right, you guys okay with this? Seems doable. It's like not too bad. And it's like, okay, it's just KQ over R, KQ over R, just sum them up. Okay. Try again. So if you guys sort of like get the idea of what's going on, everyone should be able to attack this problem straightforwardly. Give it a shot, guys. Just do it. In the figure, 8 particles form a square with distance d between adjacent particles. That's fine. What is the electric potential at point P? All right, good thing that they're asking for potential, not electric field. Otherwise, then you're going to have like 8 vectors to have need to be summed up. Okay, so what is the electric potential at the point P, which is the center of the square? All right, given that the electric field, electric potential is 0 at infinity as usual. So that's good. All right, guys, want to try this one? It's going to be quick. I was there. It's going to be quick. Give it a shot. So you want to figure out the net potential at point P. Okay. Now you start, I mean, wherever you want to start, I'm going to start from the upper left corner of this one. Okay. Let me call this charge number 1. And then just going to go clockwise, then charge number 2, number 3, number 4, 5, 6, 7, and 8. Okay. Very good. And then you could just going to start calculating potential from the charge number 1, from charge number 2, all the way to charge number 8. All right. You start seeing like how it's supposed to be done now. Then what I'm going to do is, let's start from this charge number 1. The distance that you're going to get is going to be this. Oh, what's going on here? There you go. All right. It's not straight line. Okay, do it again. Here we go. All right, that's better. Here we go. So you say, okay, Ajan, the potential due to the charge number 1 is going to be, let me use the blue color here. It's going to be K minus 4Q. Don't forget the sign, divided by that hypotenuse right there. And now because you know this is D, this distance is also D. So this is going to be D root 2. Yeah. Pretty good. So it's going to be root 2D down here. All right. Now I'm just going to keep going. I'm going to look at the next one, the number 2. The distance is going to be somewhere here from there. All right. Let me use green color for that. It's going to be K, the charge generating the potential, minus 2Q, divided by, now the distance is only D for now. That's good. And now keep going. You start seeing the trend now. So the next one is going to be 1 at the corner, upper right corner. The distance that you're looking at is going to be this diagonal again. Okay. And the magnitude of that potential is going to be K plus Q divided by root 2D. And now it seems like the process start to keep going like this. All right, let's do one more. So we have the fourth one. There you go. And then you do the same calculation again, plus K, the charge originating the potential, minus 5Q divided by the distance. And you just keep going. But when I say keep going, now you start to see that you have 2 types or 2 groups of charges that you can sort of pretty much like classify them into 2 groups. Ones are the charges at the corner, and the other group is going to be all the charges that on the side. Can you see that? The reason I want to emphasize on this, because once again, they have sharing the common factor again. All of the charges at the corner will have K over root 2D factor. And the charge on the side will have the factor of K over D. So now when you sort of like an experienced problem solver, all right, so you should be able to sort of like, okay, I'm just going to attack those charges at the corners first. By knowing that they are sharing a common factor of K over root 2D. And all you need to do is just sum all the charges at the corners. You guys with me? All right. If you like this idea, then you don't need to do all the summation for each term, and you sum all 8 terms into the final potential. You can just, okay, I'm just going to look at the corners. You have 4 charges, stay at the same distance from the point P. So all I'm doing is just pulling out K over root 2D and just sum all the charges at the corner, starting from number 1, number 3, number 5, and number 7. And the nice thing about this one that you can see is, oh, Ajahn, they're gone. So that means the net effect due to the potential, of the potential due to all the charges at the corners seems to cancel each other out. Disappear. Nice.
Okay.
Okay. And then now we're going to attack the one on the sides. So it's going to be K over D common factor. And then you just add all those charges on the side. So it's going to be number 2 minus 2Q, number 4 minus 5Q, number 6 minus 2Q, and number 8 plus 5Q. All right, minus 5 and plus 5 disappear, but now you don't have the perfect cancellation, which is fine. You should be able to now arrive at the final value of K minus 2 minus 2. So it's minus 4 minus 4KQ over D. And that is your final answer.
Okay.
See, not bad, I hope. All right. So by showing you these two examples, you should be able to see now that actually calculations of potential seems to be 50% easier, I would say. Okay, there's a question comes in. What is it mean by electric potential is zero at infinity? Okay, it means that when you are so far away, you assume that there is no influence of anything from this charge. So that means this charge will not give you any potential of doing anything due to the electric stuff. There's no field, there's no force, there's no potential. So you're not going to be able to get any potential. Sort of like that is at the level that you have zero potential energy. Does that help? Okay. Yeah. So this one came from the comment that we did last time. Let me talk about this once again. So every time that we talk about potential, in general, we talk about potential difference most of the time. It has to be potential from this point to that point, point A to point B, point initial point to final point. Okay. However, when you want to do something sort of like, well, I wouldn't say simple, but if you want to deal with something that it's like a value in its own, it doesn't seem to exist in this case. But when you want to summarize that, hey, a charge Q can generate a potential at a point, then you sort of like, okay, let's compare this potential with respect to zero somewhere. But due to this is a charged particle, the zero potential happens to be at infinity. That's all. Does that make sense to you? So this one is sort of like it's looks unusual because back in the day when you look at the MGH, you can set H to be zero level on the ground or on wherever you want. You can choose your own reference point. That's your H, right? But that usually happens when you have a uniform gravitational field. So everything seems to be like flat. It's like uniform. It's pointing in one direction. But when you look at this one, just like what we did says last time, well, the potential level, the position that's sharing the same value of the potential is in the form of a sphere. So that's why you cannot just draw like a single line in like a like horizontal line to show you the level anymore, but it's a curved sphere. So that's why it's rely on the R right here. Okay. And now to choose the zero reference, it's not like arbitrary anymore. It seems to be like it has some place that you can figure out it to be zero. And that is when R approaching infinity. I don't know, does that help or does that make even more confusing stuff? Okay, okay. All right. So that's another question, but you are never at the yeah, no. So once again, the role of this sentence saying that, hey, potential is zero at infinity is just saying that you always have a reference point. It's a reference. And that reference point is where the potential is treated as zero. Okay, so that's always the case. You never, I would say almost never, almost never. It's like, I don't know, 99.99% or whatever. You use potential energy or now potential in the form of potential difference all the time. That's what I'm saying. Okay. So all the time. For example, like a battery, When you say that you look at the triple A battery, double A battery, when you say 1.5 volts, 1.5 volts is the potential difference between the positive and the negative pole of that thing. So it's 1.5 volts. So it's just a relative potential difference between the positive and the negative polarity of this battery. Okay. All right. And in this case, right, well, just know that it's different by 1.5, but you don't know the absolute value of this one. Okay. So that's why, okay, if you want to know absolute value, let's take infinity to be where the potential is gone, 0. All right then. Okay. Maybe I just explained too much, make things more confusing. All right. But anyway, so roughly speaking, this sentence allow you to use this equation. That's what it means. Okay. Otherwise, this expression will be kind of like hanging somewhere in, in space, and it's not, doesn't make sense because it's supposed to be potential difference in the quotation mark. Difference. You need difference. Okay. All right. Try again, guys. So this is yours. So if you can do this on your own, then that should be more than enough for you to attack anything else. Try this. The figure shows a rectangular array of charged particles fixed in place. With distance A is given and the charges are given, everything is given. With V equal to 0 at infinity, once again, it happens all the time. So seeing this equivalent to, all right, you have permission to use this KQ overall, let's say. Think of it that way. All right, what is the net electric potential at the rectangle center? It's pretty much the same as the previous problem, but it's just number is going to look a little bit sort of like, is worse. Okay, so let's do that. I'm just going to draw a point P once again to be the center of this rectangle. And now you start seeing that, John, it seems like we can do the same trick again because all the charges at the corners will stay at the same separation. So we should be able to classify them into one group. So let's group that into a first group, the group at the corners. Does it sound good? All right. So we know that this distances over here are the same. Cool. I don't know why this is like act like a picking. That's weird. I'm highlighting right now. It must be a bug or something. Or maybe I just don't know how to use this. Okay. All right. So that's one group. And the other group is going to be charges on the side. And this one is down to only 2. Okay. We have only a total of 6 charges here, which is nice. Okay. Here we go. Let's attack this quickly now. You should be able to do it very easily now. Total potential at point P is going to be start from the corners, K, over the distance. And this distance right here, it's going to look a little bit bad, but not totally bad. The one on the horizontal distance is going to be A over 2. The one going up here is also A over 2. Is that right? Okay, I mean, it doesn't draw in scale somehow. Oh, that's the bottom is A. Okay, that's not, don't need to do over 2 there. Okay, so the bottom, I mean, the horizontal one is A, the vertical is A over 2. So then you can use Pythagorean theorem to figure this out. So it's going to be root, what's that? Root 5, A over 2, yeah? Okay, not bad. And that's it. Just plug it in here. Root 5A over 2 from Pythagorean theorem. And then the rest is now the row of those Q's, the charges. So you have positive 2Q1, you have negative 3Q1, you have positive 2Q1, and you have negative Q1. See, the nice thing about doing this is, once again, these whole charges go to 0. So you don't need to do any calculation whatsoever. That's a nice thing about this. Okay, so they just accidentally cancel themselves out. So good. All right, and now turn our attention to those two charges that's left. So it's going to be k over, now the distance over here is only a over 2. So it's going to be a over 2 down here. Now you only add these two charges together, positive 4q2 and not the 4q2 down there. And that's it. The net potential at point P is, K over A. Okay, let me put A over 2 down there just for clarity. And it's just going to be 8q2. And that's it. Done. You can substitute the number.
Okay.
So that's easy enough, I guess. Okay, so by having to calculate potential from point charges now is not an issue. You guys should be able to complete this task very easily. Here comes the thing. Yeah, what if you don't have any sort of like, orientations or whatever, it's just sort of like free floating? No big deal. You have already tried this with the electric fields. So let's change those questions and turn it into a question about the potential. Why not? All right. If you remember, we solved this one for electric fields already. So let's figure it out. What should happen with the potential at point P? Now things gonna be quite easy now. If you look at this one and then you can say, oh, Dan, this is sort of like nice. You want to figure out the potential at P. Now you look at space around this. Well, Dan, that one, and that one, these three are at the same distance from point P. So let's sort of like group them into a single group and then just do this calculation all in one. So it's a K over the distance. This is going to be the common factor among those three. And then you just pull out that charge, positive Q, negative Q, positive Q. So starting from these three, you already got the potential at point P of this much. Now you only left with just that last one hanging there. And that one is 2D away. Which is, well, okay, John, no big deal. I can do that. So it's going to be plus K over 2D. You guys with me? Yeah? That's 2D times minus Q. Don't forget the sign all the time. This one is negative Q. And that's it. You just add things together. K, Q over D plus, which is negative there. So it's going to turn into minus K, Q over 2D. And your final net potential at point P is going to be K, Q over 2D. And that's it. You're done.
Okay.
Clear, guys? I hope 4 problems. Now you shouldn't have any problem. Show you the problem so you don't have the problem. Solving this type of questions, yeah, or problems. So many problems right now. Okay. All right. But the things that you need to do is what happens if charges are not come in points or pieces like this. All right, this is going to be the highlights of the first half of the lecture. Are you ready? I am going to ask you how would you do this if the charge are distributed continuously, just like what we did in the potential field. I'm sorry, in the electric field. We are going to do the same thing, similar thing with the potential. We did with the field. Now we are going to do with the potential. Instead of showing you this formula, explaining this sort of like, slide and everything, just do it. Why not? Okay.
Okay.
Here we go, guys. Show me that you can. I'm going to show you how. Find an expression for the electric potential at a point P located on, it's the same setup, on a perpendicular central axis of a uniformly charged ring of radius A and a total charge Q. We did this crazily with the electric field. Remember, we have to do that vector and then it come in like a cone. You split it in a vertical direction, horizontal direction, some only the x-axis components, and then you get to the final electric field at point P. But now we only want the potential at P. So the problem about vector summation already disappeared. No vector for you to deal with. You only have to deal with the magnitude of the potential at point P. Well, not magnitude mean it can be positive, negative, zero. Okay. All right. So I'm going to show you how. Use the same trick that we did before. Why not? I'm going to slice this ring into a tiny piece first. Within this tiny piece of the ring will contain a charge dq. Good. So far, so good. And I'm going to ask you what is going to be the potential at point P due to this charge dq. You will say, Bajan, it's going to be K, the charge that generating this potential dq, divided by the distance. I can call this R for now so that I don't need to keep writing square root all the time. That's it. KQ over R is the same formula. Okay. However, because this is going to be a tiny potential due to this tiny charge, let me call it tiny potential as well, differential V. You do the same thing around this ring. So you probably can shop somewhere else. Okay, slide. This is going to contain a tiny amount of dq. All right. And it's going to generate how much potential at point P? Well, Adan is going to look exactly the same. K dq over R. So that means what you are going to do is you're just going to slice everything until you complete the whole ring and sum the potential at point P there that you just found out. So that means you already figured out the mini potential differential V at P. All you need is just sum them up around the ring. Once you're done with this, that is going to be your net potential at point P. Looks good. All right, so I hope you understand this integral terms or integral expression over here very sort of like, you know, you can relate this to the actual situation that you did with the slicing of the ring. And that's give you back this equation right here. Can you see that? So I hope you can understand this expression very easily now. And this is another way of writing the K. So I'm just sometimes I will throw you this 1 over 4 pi over 1 over 4 pi epsilon naught from time to time, just so you get, you know, some used to these two things to be interchangeable. All right, but for now, you sort of agree with this expression. Can you integrate this? Now your integrating techniques and other stuff start to creep in, just like what we did last time. But before we do that, let's pull out constants. K is constant. Actually, R is also constant. So what you have left to integrate is this. So actually, you don't need to integrate anything because the sum of all the dq around this ring will give you back the total charge, capital Q, right there. And that's it, guys. It's a K, capital Q over R. You're done.
Okay.
I can use the lower tone voice just to make you feel like this is easy. All right. Okay, not too bad. I think this is not bad. And actually, by thinking back about these problems, hindsight is like, okay, Jan, that makes sense because we sort of like learn the way that we can kind of like group them into a portion of the system that's sharing the same distance, right? When we say, oh, Jan, when they are at the same distance, we can group them together and all we need is just summing all the charges. See, actually it's the same situation here, but it just happens continuously. So as you can see, wherever your DQ is, all the DQs that you cut from the ring will share the same distance to point P. So no matter where you cut, it's going to be at a distance R away from point P, R away from point P, R away from point P, R away from point P. So what you can do is you can just group them into one group of charge. These all charges are actually at the same distance r from point P. And that's why you just say sum them up, Ajan. You're going to get the net charge, and that's it. KQ, and then you pull, sorry, there's a Q, and then you pull a common factor K over R out. Okay, so you actually apply the same trick, but now this trick is just happened in a continuous fashion. That's all. Okay, cool. Try again one more. So now you start seeing like, okay, John, sort of doable. Try this. You did this already before. In the figure, a plastic rod having a uniform distributed charge Q, everything is given, is bent just like last time. It's bent into an arc. The theta, or actually it's supposed to be phi. Sorry, guys. Phi. The figure is in phi. The phi, the angle subtaining this arc is 120, just like before, pretty much. Let's say V is 0 at infinity. So this is your ticket of using this KQ over R expression. What is the electric potential at P, which is the center of curvature of the rod? So you now start seeing what come in the same trick again. All of the charges on this arc will be at the same distance to point P, which is a radius. So you should be able to do that grouping things again. But I'm going to show you like a proper calculus way of doing this. So the way you do that is just you cut this piece into a tiny portion of the charge. Let me call it the dq. This dq will generate potential at point P by this much, k dq over capital R. You guys with me? But because this potential is still super small, I'm going to call it the differential potential at point P. Just put the D in the front just to say it's super small. And then you do the integral from the bottom to the top of this arc right here. So I'm going to cut all the way to the top. So starting from the bottom to the top, you just have to sum all these expressions. Once you're done with that, that's going to be your net potential at point P. Cool. But then as you can see one more time, wait a second, K is constant, capital R is also constant. All you need to sum up is just the total charge dq, which is as expected because all of these dq lying on the same distance from point P. So all you need to do is just pull out the K over R common factor, and then you just sum up all the charges, which is equal to, of course, capital Q. And that's it. One more time. Potential at point P is K capital Q over R, and you are done.
Okay.
So you did this before back in the day of the electric field. Then you have to remember you drew the vector, and each vector will have like directions like this, and then you do this, you do that, you do this, and then you do this, and then you have to break into two components: horizontal, vertical. Vertical cancel, left with just horizontal, do the integral, and then you get the net electric field pointing along a positive x-axis or whatever that was last time. But now, none of that happens. You only left with just KQ over R. And then, so potential is nice due to scalar's property of it. It's kind of neat, okay? And wherever you see the situation where the charges lying at the same distance from a point that you would like to calculate a potential, it looks like all you need is just summing all the charges. That's neat. Okay, so here is the sort of problems that will show up in the exam. This is the exam's level problems. Let's see if you can if you can attack this problem. All right, so we'll do this and then we'll take a break. Sounds like a plan? Okay, all right, here we go. So in the figure, 3 thin plastic rods form quarter circles with common center. Okay. Q1, Q2, Q3 values are given. What is the net potential at the origin due to the rods? Can you see what will happen now? It's just an extension of this problem right here. And seems like you now should understand, Ajahn, if you sort of like, trying to solve this kind of question, it's going to be quite simple. Why? Because if you look at the arc number 1, all of the charge on this arc will be at 1 centimeter from the origin. You move on to the next arc. This charge on this second arc will be at the 2 centimeter from the origin. And look at the third one, all the charges on this arc will be at the 4 centimeter from the origin. Now it's the same trick again. Start to let's do this. Potential net is going to be K Q1 over 1 centimeter. You guys with me? I'm done. Okay.
Okay.
Why? Because Q1, all of those Q1 is already at 1 centimeter from the point that you would like to calculate the potential. So you don't need to do any integration anymore because you already did here just to showcase how it's being calculated. So that's good. Move on to the next arcs. Next arc is going to be KQ2 over 2 centimeter. And the last one is going to be KQ3 over 4 centimeter. Woohoo. And that's it. You're done.
Okay.
You can plug in the value or whatever of your own and then just finish the whole thing. Sounds like a good plan here? Okay. All right. So if you sort of get this, let's sort of like pause right here. I think this is a good place to stop. The reason I want to stop here first, because I want this whole thing to sort of like sink in your sort of like your deep portion of your whatever brain system or stuff, and have it sort of like, sublime and blossom and everything. So, okay, so I get it. And I'm going to go full circle there in the sense that after the break, I will get sort of like take you guys back to the energy. And I hope by having shown you that, then you get the whole pictures of why do we need this kind of concept. Okay. All right. Energy is what we sort of like can be talked about more easily than potential before, but now they are going to look exactly the same. Okay. So let's do that after the break. Sounds good? All right. All right. Okay. So what I would like to sort of like give you as like a final piece of the material in this handout is go back and talk about potential energy. Even though it looks like we started everything from energy first, and when we derive, sort of like define the concepts of potential, is just the energy per unit charge. Now, I think it's time that you will be able to see the connections that most of the time we will start with the potential. I don't know, it seems like that. All right. And then you want to sort of like bring back the original concepts of energy afterward. So that's what I'm going to show you again. So let's say now if point P, okay, has the potential due to a charge Q1. So you have a charge Q1 lying around, and it's just gonna give some potential at point P. Then the question asks you again to, hey, what is the work required to bring a second charge? You have to think about this carefully here. From infinity. So when you see this word infinity again, you sort of like, okay, then that's when there's no potential. So this is the same scenario that you want to bring something from the ground up. Make sense? Because of course, the floor, you can set it to be zero potential and then you bring it up. And then you ask, hey, how much work needs to be done to move the mass from the ground up like 1 meter above the ground? Same idea over here. But this one is just a little bit hard to imagine because you have to drag it from wherever, like so far away. Okay. So the question asks you how much work that you have to provide to bring the second charge from so far away and place it at that point P. What do you think? What do you think? So I like this question. It's a simple question, but it's test your understanding about potential. So this is the same sort of like similar approach that we did with the fields in a way. Back in the day of the fields, when you want to know the force, you bring the charge, multiply by the field, you get the force. This is the same thing. So first, I'm going to show you, hey, guys, let's calculate the potential at point P due to this charge Q1 first, shall we? Okay, so You say about that, we did that already. The potential at point P is going to be K, the charge that generating that potential divided by the distance. Of course, let's name that R12 or whatever, but you can be just DRA, that's the distance. So now you know the potential at P. Back in your mind, you know this means it's the potential with respect to infinity. So your infinity is your floor. I don't know if you get my analogy over here, but that's what it is. And I'm going to drag something from the floor up to this potential. Does that make sense to you now? I hope. The floor, V equal to 0. You want to take the mass, take it up here with the distant h. Over here is mgh. But of course, back in the day of the gravitational field, you don't have the V, you have the U. So you say, well, John, this is not V, this is U. Okay, I hope this is not too confusing. All right, so the idea is now you have to drag a charge from infinity to this point. How much work needs to be done? Okay, so I'm saying you coming from VP, I mean V infinity, back, drag it to V at P. The potential difference is VP. Okay, everyone clear with this expression here. Now you want to go back to energy. We said the energy is just Q times the delta V. You guys with me? The energy change going through potential difference can be calculated by just multiply by the charge that you bring it across that potential difference. So that lead to the energy that you need to put in is going to be Q2 times V times P. You guys with me now?
Okay.
Okay. Just okay. You drag another charge from infinity to point VP. So it means this charge Q2 has to go through the V equal to 0. That's starting point, all the way up to the point where the potential is VP. If you want to know the energy, you take that charge Q2 multiply by the potential difference, which is VP, and that's it. You can now put back the form of the equation to be K Q1 over R12, and then you have that Q2 extra over here. So the formula look like K Q1 Q2 over R12. Does it look good? It looks good because it's symmetric again. It's symmetric in the sense that, I mean, Q1, Q2, Q2, Q1, I mean, you can switch the places, but it looks like this expression give you the interacting between the Q1 and Q2, just like back in the day that the Coulomb's law is trying to explain the interaction between two charges. Same over here. Okay, and that's it. That's conclude my point right here. Work is just change in the energy. In this case, is electric potential energy. And now it can be found from taking the charge, going through the potential difference that will give you back the amount of energy required to bring that charge Q2 to go through the potential difference of P, V sub P, subtract out V at infinity. Kind of like pause a little bit. So, I mean, you can add this sentence or not, doesn't matter. Okay, make sense? I don't know if this makes sense or not, but I think the reason I would like to emphasize on this slide, because back in the day that I first trying to understand this one, this is the confusing part for me. Because like, okay, it's like, okay, I need to get back to energy and how the energy is related to potential. And this is it. And it makes things quite simple. Okay, cool. All right, so I mean, just to test your understanding, answer this question one more time. Let's do it one more time. They're asking you to find the work done in bringing the 4 microcoulomb charge from so far away and place it at point P. Okay, you guys want to try it before looking at the solution underneath? I want to bring the charge from infinity and place it at point P. How to do it? Well, Ajahn, now it's going to be simple. All you need to know is just what is the potential at point P. If you know the potential at point P, you just multiply by 4 microcoulomb. That is going to be the energy that is required. Does that make sense? Okay, so let's do that. So potential at point P due to 5 microcoulomb down here and from negative 2 microcoulomb there on the right. So you just have to add these two together. Okay, so it's just going to be K, 5 microcoulomb, that's the yellow one, divided by the distance 4, KQ over R, that's from the 5 microcoulomb charge, plus K, the second charge, negative 2, negative, see, I bring in the sign as well. Negative 2 microcoulomb, micro is negative 6, 10 to the negative 6, divided by the distance, 5 meter. Good. Once you add this up, that is the potential at point P. Now, what is the work done? You would like to bring in the 4 microcoulomb charge. 4 microcoulomb charge, that's the Q in the front. Multiply by the potential at point P. That's it. You done. Woohoo!
Okay.
Isn't that good? Okay. All right. And once again, just to make sure that you know what is going on, it's the same thing as Q Vp minus V infinity. Okay. And this go to 0 as we already agreed. So the key is still in the potential difference. But now we take advantage of knowing that the potential is 0 at the distance so far away. So we can just leave the difference word and just say, oh, potential at a point. But underlying that, it's the potential difference between that point and at infinity. Okay, so what I'm saying over here is, guys, you need this much energy to bring the 4 microcoulomb charge at that point P. But now, it's just shut down on me. Oh, I didn't do anything. Okay, guys, let me share the screen one more time. It must be some disconnection here. Whoop. It's still recording. Oops. Thank you. Yeah, it's a big oops here. All right. Okay. Seems like everything is still okay. All right, I'm back. I don't know. It just disappeared. You guys still with me? It just like shut down and then restart again. Yeah, okay. I don't know. Updated or whatever. Okay. All right. So thinking one more time, just one more time. Almost done. What it's saying at this point is you need this much energy to bring the charge 4 microcoulomb and place it at point P, correct? So it's the same thing. Think about it. At point P, the potential is positive. So potential is positive means it's higher in potential. When you say higher in potential, it's the same thing as you going uphill. Make sense? Uphill. So to drag a charge from the ground level uphill, you need to supply that charge energy. So you're dragging this charge up the hill. That's it. Okay. So think about it. If some other problems, you get the potential at point P to be negative. So you're going downhill, lower, you go deeper underground, pretty much. Okay. So if your potential is negative, going from infinity to that point is going to give you negative work done. It means you're going lower, right? So it means in general, if you want to sort of like, hey, drag it down, you're not going to drag it down. You actually have to pull back a little bit, right? Because that charge is trying to go roll downhill. So you have to actually go opposite direction. So it's why you supply negative work. Does that sound good? So I'm doing the analogy with the gravitational field one more time. All right. But now we think in terms of the potential. So every time you think in terms of the potential, it's the same thing as you look at the mountain, the hill, the landscape, and everything. You can have a higher level, lower level, and the floor level is at the level where your potential is zero. Okay, so I hope this
Okay.
sort of give you a sense of what it means by potential, and that's why the comment that your friend just mentioned about, hey, can I plot this in 3D and then do this whole potential as like a 3D plot? The answer is yes, because the plot of this potential landscape will be exactly the same thing as the scenario that you like walking uphill, downhill, go to the top of the mountain, go deep into your abyss and all this stuff. That's the same idea. All right. But this is the thing is, in terms of when we speak about the charge, we define potential in addition to potential energy. So that's why you have sort of like two ways of speaking about the same thing. You can speaking about just potential alone, and then you can speak in terms of the potential energy. Depends on what you like. Okay, all right, and that's it. Let's test your understanding here, guys. If you can do this, I'm happy, and it's done. Okay, really want you to try this, and this is once again the question in the is the exam level question. This sort of pretty much came from O exam, or maybe the O exam just take from this one. In the rectangular, in the rectangle of the figure, the sides have the length given, okay, 5 centimeter, 15 centimeter. Q1 and Q2 are also given. V is 0 at infinity. Now we sort of familiar with this. It's a ticket to use V equal to KQ over R. Okay, so far so good. What is the electric potential at the corner A and B? All right, let's start from a simple one first. So let's figure out what is V at A. Well, Ajahn, that's no big deal because now you only have two charges that generate the potential at point A, Q1 and Q2. So let's do that. It's going to be K. Let's start with the Q1 over, it's going to be 15 centimeters. So let me put 0.15. Let me omit the units here. Okay, plus the potential at due to the Q2 is going to be K and Q2 right here over 0.05. Cool. Alrighty. All right. And then, of course, if you just gonna go with just Q, which is representing the number, don't forget to put the negative sign here to say that because Q1 is a negative charge. All right. So you get one number here. I think this one, I don't know, is gonna look bad or looks good. Okay, let me substitute numbers because I really want to discuss about the magnitude or the level of the potential that A and B has. So it's gonna be okay. I pull out. Okay, let me pull out the K, and the negative Q1 is gonna be negative 5 milli 10 to the negative 3 over 0.05 plus Q2 is 2 milli, so it's 2 times 10 to the negative 3 over 0.05. Here you go. All right, so let me work out this number a bit. I'm just gonna keep K as K because we can substitute K wherever we want later. Is it good number? Okay, that's not bad. So we get 10 to the negative 3 over 0.15. So let me just leave it there. All right, that's good enough. Okay, all right. That's the potential at A. So let's do it again to figure out the potential at B. So potential at B will look exactly the same except just different value. So you're going to have the contribution of the potential from Q1 and Q2 just like before, but they are just sitting at different distribution of the distances. So it's going to be K minus Q1 over 0.05 plus Q2 positive times K over 0.15. Okay, you just swap between 0.05 and 0.15. That's all. Okay, I can pull out a common factor K. You have negative Q15 times 10 to the negative 3 over 0.05 plus 2 times 10 to the negative 3 over 0.15. There you go. All right, and for this one is, okay, that's a number, looks good. That's not bad. It's bad. It's negative 13. All right, but anyway, that's fine. We don't need to get to the final numbers or anything, but just enough to see what is the difference between A and B. All right. Does it look good? Is my number, okay, are my numbers correct? Okay. Okay, that looks good. All right, so what you're seeing over here is now you're already done with part A. You know how to calculate potential at A and at B. That's no big deal. Here's the kicker. What about part C? I would like to bring a charge, the third one, Q3, from B to A. Here we go now. I'm starting here with my Q3 in my hand. I want to drag this Q3 from B to A along the diagonal of this rectangle. How much work do I need? Give it a shot, guys. Just kidding. All right, if you can answer this one, that will be super cool. And that means you understand the whole concept of potential and potential energy, I think. I would like to drag the third charge, Q3, from B to A diagonally. How much work do I need? It's not going to be so far away from what we have already done. All you need is just the potential difference. You guys with me?
Okay.
You got what I'm saying here? Because if you imagine what the potential is just landscape telling you what's high, what's low, right? It's like mountain, terrain. So from what you already calculated, it looks like point P is low because it has a negative value in it. And it looks like A is high because it's positive. So it looks like B is deep, A is higher in level. Think of it in terms of altitude, ความสูง, yeah, altitude. So you know in your head, dragging from B to A will require some energy because you're trying to bring a charge from a lower to a higher place. And because the charge that you are dragging is positive, so you don't have to flip the sign or anything. So everything should be just like your intuition. So when you want to drag a positive charge, it will take some energy to bring from a lower potential to a higher potential. How much? Your answer is going to be just the amount of energy that you put in. It's just going to be the same as, I'm sorry, just say one thing, right? One thing. The amount of work done, which is the energy transfer, the amount of work that you have to supply to the charge is going to be the amount of energy change going from B to A. You guys with me? But now you can calculate the energy change by taking the charge that you want to sort of bring and multiply by the potential difference between those 2 points. Okay? And when you want to do that, it's just saying that because you start from the point V, you end at point A. So final minus initial. You guys with me now? So that's why I sort of emphasize so much about when you talk about the delta, it has to be final minus initial points all the time. And from here, then that's it. You already had all the information in your hand. Q3 is known. That's 3 microcoulomb. V at B is just right here. V at A is just right there. So all you need is just plug in these two values. It's K 10 to the negative 3 over 0.15. That's V at A. Subtract, as you can see, is a negative K 13 times 10 to the negative 3. It looks really dirty here. Sorry. 0.15. There you go. So many parentheses and brackets here. But I think you get a point. The point is the final number will always be positive in this case because you are dragging a charge from a lower level, lower altitude to a higher one. So you need to supply this charge some energy to drag it uphill. Does that make sense? Okay, so your mathematics takes care of the sign automatically because your final potential is higher than the initial. So the difference, potential difference is positive. So you want to walk uphill, give this charge some energy so it can walk uphill. Okay, so there's a question comes in, what if the charge Q3 is neutral? Then it will require no work. Correct, that is good. If there's no charge, you won't feel the effects from the electric fields or electric potential. So there's no work done due to the electric field or electric charge or electric potential, depends on what you want to talk about. But without the charge, you don't have any influence related to electric whatsoever. Okay, sounds good. All right, you need Q to be either positive or negative for that charge to feel or can interact with the electric field from environment. All right, so I hope you, I think this is a very good exercise of showcasing what we have been doing in terms of the talking about the potential and potential energy. If you can answer this one, I think this is very good. However, all right, I don't want to put more material into whatever we're going to talk today because I think I just want to focus on the potential. All right, and the next sort of like concept in the next handout is going to be something, it's kind of new, and I think it's going to sort of mess up what you're trying to understand today about the potential. So what I would like to show you is this. You guys, could you go to that site one more time? The PHET. So I'm going to give you the link. Oh, where is my link? Okay, give me a second here. All right, so I'm going to give you the link and you guys can sort of go there along with me. Oh, I think I lost that link. Okay, give me a second here. All right. I don't know why this website is very slow now. It's like it's, I don't know, it's so far away from us somehow. The server it has to load and load and load again. Okay, I'm getting there. Okay, all right, here we go. It's this one here. All right, I'm gonna paste the link in the chat and you will have a chance to go there too. All right, guys, try this out. So it's once again, it's a simulation that we are able to do. And I think I can share this screen instead. Okay, let me share the screen. All right, I'm gonna pop out from that. Here we go. All right. Okay, can you see this now? I hope. All right, and it's a HTML5, so you can just run it right away. Already. All right, so this is a simulation trying to showcase what we have been doing in the past about fields and potential. So I'm going to mimic that problem that we just did. What we just did was we have two charges at the corner of a rectangle, right? So what I'm going to do is just I'm going to place, I think it's a negative charge on the left. Oh, I don't remember. What was that one? Okay, here we go. So there's a negative charge on the upper left corner right there. Okay, but that's just a good thing. So the good thing is, can you see these arrows around this? Okay, you can see the arrow. That's kind of nice. So these arrows actually giving you the directions of the electric field. So what I'm saying is, can I trash this one for now? Oh, it's already there. I have to restart. Okay, so once you place the first one there, see, that is the electric field that's going outward from a positive charge. Okay, and this one, they are not sort of like showing you the line or anything. They just give you a vector field. So this is very good. And the intensity or the brightness of this arrow will give you the strength of the electric field. So as you go further away from it, it will get sort of fade away because of 1 over r square factor. Sounds good? All right, and what you can see over here is, all right, where I, oh, okay, option is being blocked. Okay, here you go. And what you can do next over here is I can show you the voltage. See, isn't that cool? So when you look at the voltage here, the wherever is super red is mean is high. High means the potential is high. Voltage is the potential energy. I'm sorry, it's a potential. So when the red is super red, it means you're already super high. And when it's sort of like, okay, sort of fading away, it's getting black. So that's, you are very close to zero. Does that sound good? To make it even clearer, there is a device here that you can drag and see that it say equipotential. So you can guess if I draw the place where the potential that's going to be the same. Let's say if I can figure out the 14 volts location, and I just want to draw everywhere that the location has the 14 volts. See, it's going to come in a circle. And this one is exactly what you saw as a sphere around a charge. Does that look good? All right, so if I want to look further, I'm going to just getting further away. Of course, this is going to be a lower potential. Let me find out where it's about 10. I draw another line. I can go out and let's take like 8. If I can figure out 8. 8. 8 somewhere here. Okay, good, close enough. All right, 6. Okay, I keep going. 6 volt around. Oh, that's close enough. Let's go 4. It's going to get further and further apart because you know it's 1 over r relationship with this. Oh, there you go. 4 there. All right, and this, because I go in a step up 2, I should draw 12 here as well. That's 12. That's 14. And 16 is going to get squeezed in. It's going to get closer and closer. There you go. That's close enough. And then if I go 18, all right, you guys can have fun with this, doing it on your own. There, something like that. So those green lines, can you imagine this is like an altitude map? Or you can name it like a contour map. And this one, you can see that at the peak, which means at the center of this one, you are at the peak of the mountain. It's super high. So I can actually show the value here and they will look closer to an altitude map. It's just like when you look at the map and this one is like the top of the mountain is right here. And then it's sort of like going downhill from the center of the mountain. Does that look good? All right, so I think you get an idea of what it means now by the green lines always cut the electric field in the perpendicular direction, just like what we talked last time. Cool? Okay, and that's it. That's what I would like to show you. Not that's it. That's what it means by the relationship between the electric fields and the electric potential. And what does it mean when I say there's an uphill, there's a downhill? Because, okay, let's try again. I'm going to add a negative charge now, and we're going to redraw everything one more time. Look back at our problems here. I have Q1 on the upper left, and Q1 is like, let's say about, it's 5 microcoulomb. Q2 is about 2 microcoulomb. So upper left corner, it seems to be like twice is 2.5 times. So I'm going to double this. I'm going to press 2 of this here. It's about 2.5. So just to make it a little bit more dramatic, I'm just going to place 3 here. Okay, let me do this. I'm just going to do 5 here. I'm just going to do 2 here. All right, just to make the ratio exactly the same as what we saw in our problem. Sounds like okay? All right, so I have 5 units of charge on the upper left, which is negative. I have 2 units, even though it's not the same exact thing, but the ratio is going to be the same. And the 2 units of charge, which is positive on the lower right corner. Okay, so let's figure out what is happening around this. So let me draw some of the equipotential energy. It's going to look like this. All right, I'm just keep drawing somewhere in between. Keep drawing. And now you start to see that you are building up a contour map. Even though this one, the spacing between each line might not be exactly the same, but I think you get like an idea on what is happening around this. All right, I think this is good enough. I can do one more here if I like here. All right, okay. All right, so that's what it is. Can you see this? So what you see is you can see that the electric field sort of starting from the lower right corner, the positive charge, and it's curved and it's going to sink into the negative charge on the upper left. And if you look at the color, the red, it means it's higher. The blue is actually is deeper. Let's say it's lower than 0. The more blue you get, the deeper you're getting. And if you look closely here, if you imagine this is your rectangle, this is where we're sitting. So I'm just going to put a sensor right here. Yeah, there, right here. See, that's where the electric field is pointing to. And you have the location of the electric potential and the field. But over here, you are still in the region of blue. So that means this is exactly the V at B in our problem. You have a negative potential here. And then can I place another sensor here? I can. So I'm going to pick upper right corner up there, see? So the arrow will give you the electric field at that point. But this is sort of in the region of red. It's kind of reddish. So this one, I am sitting on the potential point where the potential is still positive. So can you now relate it to what we sort of just did in the problems? You starting from here, you try to go up to here. I mean, can you see my arrow here? We're starting from upper left corner here, and you want to drag a charge uphill to this point right there. That's why you need some energy, because you're going from a deeper than the 0 level. It's in the blue, it's lower than the floor, the ground level. And then you try to bring this charge up into the mountain on the right side. Okay, does that help a bit?
Okay.
All right. However, I didn't comment about Ajahn. Wait a second. They want you to drag this charge diagonally. Why didn't you care about the directions of the traveling of this charge? Remember what we just commented, saying that the concepts of energy, this type of energy is electric potential energy, is independence of path. I can talk again and again and again about this, right? You're starting from here, you can bring this mass up, or you can do this zigzag, or you can throw to the right and bring it back here. You can do anything with it as long as you're starting at the same position, you end at the same positions. Then the difference between these two positions will be exactly the same in terms of the energy difference. Same thing over here. You don't need to drag this charge diagonally. You can drag the charge wherever, whenever, however you like. You're going to end up with the exact same amount of energy that requires. Does that make sense? All right, because if you want to go around the hill, that's fine. That's your choice. But you're going to gain some energy at some point. You're going to lose some energy at some point. Once you sum them up and you end at the same terminal point, the total energy that you spend is going to be exactly the same because of the independency of the path. All right, so that's what I need for today's lecture. Sounds like fun.
Okay.
All right, guys, I think that is it for today. But I think this simulation is good. So if you have a chance, try it a little bit further, or you try to mimic or simulate some of the problems that you see in our class or in the homework and stuff, and then you can see if you can relate to the actual electric fields and electric potential drawing thing. All right, and just to answer part of the question that your friend just asked, this one is a contour map. So you're trying to put a 3-dimensional mapping, I mean, sort of like surface, 3-dimensional surface, and place it on a 2D map. So that's why you get a contour with a label saying the height. Okay, but if you want to plot in 3-dimensional space, you're gonna get a mountain and you get like a valley and everything, just like an actual 3-dimensional surface. Yeah. Okay, guys, any questions I hope this helped a little bit. Yes. All right. Okay. So if this is good, then I put the next homework set already in our Google Classroom, so you can check that out and just give it a shot and see how you do with that. Okay. And if you have any further question, then we'll have a chance to chit chat and talk about those problems later. Okay, guys. Thank you for today, and then I'll see you next week. Yeah, and then I think next week there'll be one makeup session, and then we'll leave one session for the review and Q&A. Okay. All right, guys. Take care. I'll see you next week. Bye bye.
Okay.
Question.
You like this one? There's no need to keep
Yeah,
it.
get one.
Oh, on this one.
Uh,
Okay, I'll leave it there.
But new. I want you to create a new one.
Oh, okay. Got it. Okay.
Uh,
1 second here. What is going on with? Okay, let me.
Refresh.
What I am doing.